Hey guys, it's Booth Dog here. Um, I'm doing well. I hope every single one of you is also. I hope you're doing well. Your families are well. I hope everyone is safe. I hope you're staying safe, staying in, not going out. I hope you're getting everything you need. Um, these are interesting times. I know you might be feeling anxious, unsure. Very normal. We're all feeling that too. Um, But just know that there's a lot of work going on behind the scenes to continue to make sure that all of you are going to get the best education opportunities as humanly possible. Um, I think crises like this tend to reveal a lot about who we are as people, as a community, as a school. And so you're learning a lot about your teachers, you're learning a lot about each other, your family. I think you're going to get the chance over the next couple of weeks, hopefully just a couple of weeks, to see a different side of your teachers. I'm not wearing a tie. I'm wearing my BB-8 shirt. You're going to see us a little more relaxed at times, I think. That's good. Just know that we're also working pretty diligently. Okay, so in a second, this is going to transition. You are going to hear a lecture not from Booth Dog, but from Mr. Boothman. And he's going to tell you all about today's lesson. We're working hard, and that means you do need to work hard as well. Okay? This isn't going to work if your teachers are the only ones putting in the time and the effort and the energy to this. Part of it needs to come from you, and that's fantastic training for college and what college is going to be like. Very self-directed, very self-disciplined. Are you checking in on the things you need to check in on? Are you doing things without being reminded 20 times? These are really good skills for you to develop, and I think that is one good that can come from this. But it's going to reveal which of you don't have those skills, which of you don't want those skills. So I genuinely hope that you're taking this seriously. I hope that you enjoy Mr. Boothman's lesson. As dry as it can be at times, I do apologize. But keep it up, do your best, stay safe. Here we go. All right, so let's go ahead and get started. Okay, so this will be section 8.3. And this is volume of solids. All right, so before I actually jump into explaining volume of solids, I want to take a second and what would have been our warm-up question, I still want to think about it. What exactly does the integral represent? Okay, so the integral itself, we know, represents the area under a curve, the accumulation of change. And how exactly does the integral calculate this? Okay, so we started this semester really by talking about LRAM, RRAM, MRAM. Okay, so using rectangles to approximate the area under a curve. And then we got a little more refined and looked at trapezoids, trapezoidal rule. And ultimately, we ended up using this idea of a limit and adding up an infinite number of rectangles underneath each curve. And calculating this will actually give us the exact area under a curve. So to find area, we're adding up an infinite number of rectangles. How can we take this and use it to find volume of something? Is volumes, singular. How can we take the integral and use it as a tool to calculate the volume of something? Okay, well, if we think about some shape, and I'm going to do my very best to try to draw this on this board, let's just start simple. Okay, so it could be better. So we have this cube, okay. how can we find the volume of this cube using this integral, using an infinite sum? Well, we know the area of this piece, right? That's a square. Okay, so we know the area of this. So if this is length s, then this area in here equals s squared, because it's a square. And if I take what we call a cross section, so this is going back to geometry, but imagine slicing into this right here, just at any point in here. Okay? If I slice into this right here, what shape would I pull out? I would pull out this square. Okay, and what's the area of that square? Okay, again, it's s squared. And how many of these little squares, how many of these cross sections can I find in this cube? The answer really is an infinite number of them. I can slice this cube, just like we slice area under a curve, into an infinite number of rectangles. I can slice this cube, or any shape really, any three-dimensional shape, into an infinite number of these cross sections. And if I add up this infinite number of cross sections, what do we get? The volume of the shape. It's the exact same thing we're doing when we're finding the area under a curve. We're adding up an infinite number of them. And I'm going to keep saying that because it's such a weird idea, but I really want it to start sinking in. So what exactly does this look like? Okay, I'm going to pull out my trusty notes. Okay, so hopefully, should have prefaced this at the start of the video, I have shared your 8.3 mastery sheet. Okay, so that will be practice problems, and we'll go through a couple of them together after we talk about these notes. But I know you don't have your binder probably with you. Hopefully you have a notebook, you have paper, you have something you can take notes on, okay? That active writing, it is very important. Hopefully you just have some scratch paper and you can take notes there and then add it to your binder once we get back to our classroom. So please, whatever you have to take notes on, pull that out now. I'm going to give you some definitions and some formulas to copy into your notes. Okay, so again, 8.3 volumes of solid. And here we go. Okay, so the volume of a solid with a known integrable cross-section area A of x from x equals a to x equals b is given by the formula volume equals the integral from a to b of the area of that cross-section taken an infinite number of times. Because what is the width, what is the depth of each of those cross-sections? As we take this limit as we approach infinity, that depth approaches zero, and which is why we're talking about taking this infinite number of them. Okay, so again, write this down. The volume of a solid with a known integrable. Integrable, it's like the word differentiable. So differentiable meant we had a derivative exists. Here, integrable means we can take an integral, we can take an antiderivative. The volume of a solid with a known integrable cross-section area A of x from x equals a to x equals b is given by this formula. Exactly like area under a curve. This is finding the volume. So let's talk about, I very rarely give you steps, but let's talk about some steps we can take to approach one of these problems. Okay, so step one, sketch the solid. And a typical cross-section. So just like we did here, and I know I'm a very bad artist, but here it is. We sketched the solid, we sketched the shape of this cross-section. Sometimes these cross-sections get a little weirder. Okay, so this definitely does help. Okay. Find a formula for the area of that cross section for A of x. And lastly, find our limits of integration and solve. Okay. Let's look at an example. Let's talk about the volume of a pyramid. Pause this if you need to finish writing down these notes, but I'm going to move on. So, example. A pyramid of height 3 has a square base that is 3 centimeters on each side. Let's see. Each cross section is a square. Find the volume. All right, so let's start by sketching this solid, trying to come up with a typical cross section. Okay. All right, so let's draw our pyramid here. I'm just, bear with me. All right, so there's our pyramid, and it's extending something like that. Hopefully that's okay. Now we're told that the base is 3 centimeters long on each side, and it extends out with a height of 3. What is the shape? So if I slice into this at any point, so just right here, okay, that's a square. Okay, and what do we want to call the side length of this square here? Let's just call it x. Okay, so what is the area of this square? The area of this cross section? X squared. So what is our volume? Okay, so we sketched the solid in a typical cross section. We found a formula for the area of the cross section. Okay, we need the limits of integration. We're starting from a height of 0 all the way up to a height of 3. And our a of x here is x squared dx. Take the antiderivative. Okay, and we should get, plug in 3 cubed divided by 3 is 9, minus 0 is 9 square centimeters. And there we go. Well, if any of us happen to know the volume of a pyramid, you might know it is 1/3 side cubed. I'm using x instead. This is really where a lot of our geometric formulas come from. Okay, we take an integral. So that's kind of as much as I want to put into your notes today. Again, I've shared your mastery sheet. Go ahead and take out that mastery sheet however you are accessing it. Okay, I recognize not everyone is able to print it. Okay, that would be ideal, but again, I know that that's not, that's certainly not an expectation of each of you. I do want to go through the first question on that first page of the mastery sheet together, and then I will ask you to work on a couple more for the rest of today. Okay, so let's look at our mastery sheet. So looking at the directions, it asks us to find a formula for the area a of x of the cross sections of the solid that are perpendicular to the x-axis, and set up the integral that would solve for the volume. Okay, so for this first problem, They kind of drew it out for us. The solid lies between planes perpendicular to the x-axis at x equals -1 and x equals 1. The cross sections perpendicular to the x-axis between these planes run from the semicircle y equals -√1 minus x squared to the semicircle y equals √1 minus x squared. A lot to unpack here, and even more so, part A, there's an A, B, and C here. The cross sections are circular discs with diameters in the xy plane. Let's take it one step at a time. Here's our xy plane, okay? It's this flat board. We are looking at a solid that extends from x equals -1 to x equals 1. The cross sections are going to be perpendicular to this plane. So at a right angle to this plane. So imagine my hand right here is a cross section, okay, sticking out from this plane. Now those cross sections run from the semicircle y equals -√1 minus x squared to y equals +√1 minus x squared. Hopefully some of us are thinking, oh, what shape is that? The reason we're splitting that up into two semicircles, it's actually one full circle. Okay, that circle is actually given by this formula. But is this really a function? No. So to make this a function, we solve for y. When we take that square root, we get positive and negative. We split that up into two separate pieces so we can talk about it as a function. But really, we're looking at this. Okay. This top part would be the positive square root, and this bottom part would be the negative square root. For part A, we're told that the cross sections for this are circular discs with diameters in the xy plane. Here's where I'm going to try to get a little fancy. Let's see how this goes. All right, so we have circular discs. I just discovered what's even more annoying about our spam calls is that it stops your video from recording. So let's try this again. Here's our base. We have a circle. Again, it's two pieces of the circle, so we can talk about it as functions, the top half and the second half, right here. Here's our cross section. I know it's not actually a circle. Imagine with me that it is. And its diameter is sitting on this board, on this xy plane. So if you can imagine, this circle, if it could, would pass through this board. Okay, and I'm going to fold it in half since I can't actually slide it through this board. And it's sitting right here. Its diameter is on this plane. Now we know our volume is going to be the integral from -1 to 1, right here, of the area of one of these cross sections, the area of one of these circles. Well, what is the area of a circle? Pi r squared. We just need to find a way to write this as a function of x, right? We're integrating with respect to x. We have limits of integration that are x values. We need to express r in terms of x. So let's go back here. Here's our cross section. Here the radius would be then, right here. That's r. How can we write that as a value of x? Well, isn't this right here, this height, just our function value for that given x value? Let's think about that a little more carefully. Whatever this x value is, I'd plug that into this function and it would give me this y value. It would give me that height. And since it's a general x value, it doesn't matter where this r is, it doesn't matter what I'm plugging in, I'll just get whatever our height is at that value. So our radius here is just this function. And again, that radius is being squared. Square root squared cancels out. And so our volume is the integral from -1 to 1 pi times 1 minus x squared dx. And we don't actually have to evaluate this. Okay? We were only asked to set up the integral. And that's going to be a common thing for most of these problems. Set up, but do not solve the integral that finds this. So we're done. Now, everything I just went through was kind of a lot. It's okay if you have questions. You can always ask me during our Q&A time. Send me any other questions you might have at any other time. This section is just difficult because it requires you to visualize these things so much. Even if we were in our classroom, if we were in the room together, it would still be hard to explain this on a flat board. Okay, so I hope this kind of helped. Watch all of that again if you need to. Okay, write down your questions. I'm here to help. There's a reason I gave us a lot of time in class on this section. I would like you for today. Okay, so that's basically it for notes today, and that's all I'm going to go through. I would like you now to look at part B. So this was part A, now part B. It's the same base, but now it's telling us that our cross sections are squares with bases in the XY plane. So here's a square, here's a cross section from somewhere here, and its base, so it's not going through, its base is sitting right here on this shape. So here, for part B, here is our cross section. Okay. And a bunch of squares are filling this in. And for part B, the same general formula. We're integrating from -1 to 1. But our a of x formula is going to change. Okay. What is the area of a square, and how can we write that area formula in terms of x? I'd like you to try that yourself. In addition, once you're done with that, I would also like you to look at the next column and look at part A. So for the next column, it's a very similar exercise, but instead of this circle being our base in the xy plane, it's actually going to be a sideways parabola in the xy plane, and then we'll have different shaped cross sections on that or through that. So just part A in that second column, those two questions, I want you to try them. Tomorrow we're going to finish this first page, really taking our time here. So again, rewatch any parts that were confusing to you, send me any questions you may have, and then I'd like you to do part B in the left column and part A in the right column. And we'll look at the rest. I know I skipped part C, and then we have some more in the right column. We're gonna look at that tomorrow. Okay, so take your time, you'll be okay. All right, that was it. I hope you enjoyed today's lesson. Again, I will be available to video conference on Google Meet from 11 to 12 today. As we go forward, I'll reevaluate that and see if there's better times, if I need to be available a little longer. But we're being flexible for now. Okay, so 11 to 12 if you have any questions you need to ask me. Otherwise, feel free to email me. You know, I try to respond pretty quickly, and we'll go from there. All right, so thank you so much. Wash your hands. Stop touching your face as I touch my face for this entire video. Be careful.